Hello and welcome back to another video. Today we're going to be doing Trigonometry 2 about the Steradian measure and some other side topics that are pretty important and cool to look at. So, topic 1 of 7. We have a review. So, if we draw a unit circle, let's say this is a unit circle where the radius is 1, we can have angles that are smaller, like so, or bigger, like so. We can represent the arc length of the angle, in terms of theta. Now, we can divide circles into 360 parts, and each of those parts is known as a degree, but we can represent it in terms of theta. And that's what we call radian measure. And we can figure out, judging by the area of this arc, what the angle should be. Now we're going to move on to topic 2, which is how we find the circumference of a circle. Now, circumference is known as 2 pi r, but we're going to prove that. So, if we draw 3 lines, each getting longer than the other, we could bisect each of these lines into a circle, where that line is the diameter of the circle. So in that sense, the circumference of the circle would be proportional to the diameter. Now, we can rewrite this as the circumference is equal to k, which is our factor, and d. So the circumference is equal to this proportionality factor times the diameter. Now, let's say in this case, in most cases it'll be pi, so it'll be pi d. So then the circumference of a circle is 2 pi r, since the diameter is 2r. Moving on, topic 3. We're going to discuss how to find the arc length of the circle. So, if we have a circle here, right? And I'm going to draw it into quadrants, like so. And we have this angle. Let's say this is the angle, and we're going to refer to the arc as S. Okay, let's say this is the angle. The arc will be referred to as S. And this is the radius of the circle. What we can do is draw a unit circle inside of this with a radius of 1, smaller circle, where this degree is theta. Now, we can represent this as the arc over the diameter. So we'll have S over 2 pi r is equal to theta over 2 pi 1, since we know the radius is 1, but we don't know this radius. So that would mean that after we do some canceling, S over r is equal to theta. We can differentiate this in terms of time, so d over dt s is equal to d over dt r theta. And this arc, in proportion to time, we can refer to as the velocity. So the velocity of r d theta over dt. So we can find it by referring to velocity as r omega. Well, we can refer to it as r omega, and that is our solution to that. Topic 4 is our main topic of this video, the Steradian measure. Let me write that out for you. Steradian measure. Okay, so we're going to take what we did in the previous problem and we're going to expand it to 3 dimensions. So instead of a circle, we have a sphere. I'm not very good at drawing spheres, so I apologize for this, but we have a sphere. And what we're going to do is we need to find the arc of, let's say, this cone. So in the 2D problem, it would be an arc. But in a 3D problem, it turns out it would be a cone because of how the points would have to come out from the center to the radius. So we'll refer to this as R, and the surface of this is A. Now again, what we're going to do is we're going to draw a unit sphere inside of this. And now we can refer to this length where it intersects the unit circle right here as omega. So basically what this would mean is if we take this as a fraction of A, we find that A over 4 pi r squared, which is the total surface area of a sphere, is equal to omega over 4 pi times 1 squared, since again, radius is 1. We cancel that out, and it comes to A over r squared is equal to omega, which we can rewrite as A equals r squared times omega. So now we know how to find both an arc section and the area of cone section on a sphere. And now we're going to add some different topics, and then we're going to tie this all together. So topic 5 is on the Cavendish experiment. Okay, so basically, let's say we have a roof here. This is the roof of, say, like a house. And we suspend from the roof a metal bar that is hanging by a piece of wire. And on that metal bar is a mirror. On each side of the metal bar, we have two objects. Object M1 and object with mass M1 and object with mass M2. And next to these objects, we have identical versions of the other one. So we'll have M1 and M2 over here, M1 being on the bar, and over here M2 and M1 with M2 being on the bar. And what the experiment states is that if we, let's say there's a light source here, and this light source shines into the mirror and bounces off to here, let's say. Now, the closer we move these two objects, the closer their gravitational field would pull them together. In other words, we could spin the bar by slightly moving M1 and M2. And what this will do is, as the bar spins, it'll re-angle the mirror, making the light bounce to somewhere around here. And in measuring this distance, we can figure out the force at which the bar is moved. In other words, we can figure out the force of gravity. And this is represented by the equation force is equal to the universal gravitational constant times the M1 and M2 divided by r squared. And that is how we get that formula. Topic 6. This is going to tie into topic 7, but it doesn't really seem like much on its own. But it's still a pretty good concept. Let's say we have the Earth. This is the Earth. And let's say we have 3 people on the Earth's surface. We have one up here, one here, and one inside of it. So one above the surface, one on the surface, and one inside the surface. Now let's say they all weighed the same standing on the surface, and then they each went to these points. Which person do you think would weigh more? Now, intuitively, you would either think it would be this guy or this guy for each of their respective reasons. But it's actually this guy who would have the most weight. This guy up here is farther away from the Earth's center than the other two, meaning that its gravitational pull is weaker than the other two, so he would naturally weigh less. But wait, you say, by that reasoning, this guy would weigh more since he's also closer. Well, the mass of the Earth itself has some rocks above its level. For this guy, he has, all the rocks since he's above the surface. But since this guy is below the surface, there's some area that is just above him. And this little area here makes it so he weighs less than the other two. Or at least less than the person on the surface. So now we're going to tie everything we've looked at together, and we're going to prove that if we were to magically hollow out the Earth, there would be no gravity in the center. It's going to be topic 7. I'm just going to call it Hollow Earth. And so basically what this would state is if we have, the Earth's surface, and we were to hollow out the inside here, you could be able to go inside of the center of the Earth, and you would just float around. And the reasoning for this is that if we were to equally hollow it out, we would be pulled in all directions constantly, making us weightless, in a sense. Or feel weightless, anyway. So, we're going to assume that we hollowed it out to the point with a thin, uniform shell of matter that's the same matter. If it's different matter, it can throw off the gravitational pull. But let's just say it's all the same material, and we just have a thin, uniform layer of it. Let's say it looks something like this, where this is our thin, uniform layer of matter, and inside of this is hollow. If we were to pick a point, or an object, let's put an object with mass m, and we draw 2 lines making cones onto the edges of the Earth. Now, technically, yes, this would be 3-dimensional, but I'm drawing it in 2 dimensions just to make it easier to see. Each one of these cones would reach out to a point on the surface, and it would create a little cone with its own area. We're going to call these Area 1 and Area 2, with their own respective masses, M1 and M2 respectively. Now, this shorter length here we're going to call R1, and this longer length R2. So now we are going to begin our proof. So as I said in the earlier one, we can represent the force with gravitational pull with the formula G mass 1 mass 2 over R squared. Here's how we would do that in this case. The force of one of the cones over the force of the other cone would be equal to G, the mass of the area formed by the one cone, and the mass of the object, over this radius here, the length from the mass to the edge of the area, R1 squared, over the exact opposite. Gravity times the second mass times the object over R2 squared. We're going to multiply both sides by 1 over Gn. And then we're going to get the formula capital M1 over R1 squared over M2 capital over R2 squared. This is equal to sigma A1 over R1 squared over sigma A2 over R2 squared. We can multiply both sides, or the entire thing, really, because they're over each other. We can multiply the entire thing by 1 over sigma, and that leaves us with A1 over R1 squared over A2 over R2 squared. And we've already shown from our previous thing that this is equal to omega. And omega divided by omega, anything divided by itself is 1. In this case, omega is this angle here and this angle here. Now, we don't know the value of omega, at least as far as our numbers go. But any number that is the same over itself is equal to 1. And since it's 1, that means the force for both sides is equal. And we could do that anywhere on the circle, or technically a sphere, proving that the inside of a hollow Earth would be weightless. Bye, guys.